So we're going to change gears now a little bit. There has been quite a lot of talk on OpenACC and on the way how to accelerate an application with GPUs without changing the control flow of the application too much. So what we're looking at now is how to get the best performance out of the GPU if you're willing to actually write code for the GPU yourself, so by programming in CUDA. Just to give a brief overview, I mean, you have the outline of what's going to happen during the rest of the afternoon or of today. Basically, this first 1 hour presentation is going to be basic CUDA. We do a little bit of hands-on work because I think it's important that everybody has at least once in their life written a CUDA program, a small one by hand. So it's not going to be very exciting, but it's just a little exercise. And then in the afternoon, we talk a bit more about Kepler, so the device that's currently installed in the XK7, Kepler and CUDA 5, which is the latest CUDA version, what kind of features it has, and so on. And then after that, we will talk a bit more about debugging tools, performance analysis tools, and so on. I'm not at all committed to the schedule. So if you have any questions, or if you have any particular pieces of information that you're keen on, let me know. This is your time, and you should get the most out of it. Okay, right. What on the NVIDIA side, the way that we view the programming environment for GPUs is basically put on 3 pillars. One of them we've been talking about extensively is OpenACC, which is kind of in between low intrusion and maximum intrusion into your application, or maximum flexibility, if you want to use a euphemism. Programming languages, that's what we're going to talk about is with CUDA. But keep in mind, there's a lot of libraries out there that have been developed for GPUs specifically that may already be solving the problem that you have at hand. This is just a few of those put out, of those libraries that are currently available. Many of them are provided by NVIDIA itself, like cuBLAS comes with the toolkit, cuRAND for high-quality random number generators, for sparse linear algebra, what else? FFT. So for many of the very basic algorithms, there's libraries that you just plug in and they run on the GPU. And then there's more specialized ones, like the Visipl, which is a image processing library, and commercial ones as well. So there's a zoo of libraries out there. So before deciding to write a lot of code yourself, please go out and have a look at these different libraries. Oh yeah, actually there is. Yeah. Ah, cool. So now when talking about CUDA, it's important to first figure out what is the actual model, and then only later on dive into the syntactic elements that are being introduced. So first, I just want to talk about the overall model. This is somewhat of a repetition what Alistair has already mentioned yesterday, but it's so fundamental it might be helpful to just hear it a second time. So what is CUDA? Actually, since CUDA was introduced, there has been a shift. Originally, it was a subset, well, it was C with extensions. And somewhere in the various versions of CUDA that have been released, it has moved to C++. So the NVCC compiler, the CUDA compiler, is now a full C++ compiler. CUDA itself is C++ with some extensions. I know that, whatever, it was about 50% of the people here are native Fortran speakers. Fortran support at the moment is only via mixed language approach, or alternatively with the PGI compiler that has a Fortran CUDA, its own CUDA Fortran standard. The goal of CUDA is to scale to hundreds and thousands of threads, but without having to worry too much about the details of how then these threads interact with each other. So the developer is still focusing on a sequential program that they're writing. And as I said, CUDA defines not only the programming model, but it also defines some of the architectural concepts, like the actual memory model. So how does a CUDA application look like? Well, it consists of a single source file or multiple source files, but you basically have an interleaving of serial code that runs on the host CPU, and parallel code that is then being farmed out to the GPU. The parallel code executes on the GPU, and it can be one or multiple ones. That's then up to your particular application. The code that runs on the GPU is called a kernel. And the entire GPU executes many kernels, or it executes one or a few kernels with many, many threads. So a thread is an instance of a kernel running on the GPU. Now these threads are not the same as the heavyweight POSIX threads that you have on the CPU, but they are basically just individual lanes in a vector instruction that are being executed. So again, just for the terminology, we talk about the CPU or the host, and the host executes functions. And we talk about the GPU or the device, and device executes kernels. So depending on what you're listening to, you can already, when we talk about the kernel, that it's something that executes on the GPU. So we've covered that the kernel is a function that is being executed, and it's executing an array of these threads in parallel. Each one of these threads has a way to identify itself. So basically to identify the array index. In CUDA syntax, it's called thread IDX index, which is a three-dimensional struct that, and the X component is the first dimension of the thread index. Now all threads that execute a kernel execute the same code, but they can take entirely different paths through this code. So you can branch based on your thread ID. You can perform entirely different operations based on your individual ID. Now, whether that performs well or not is a different question, but you can do that. So that simply means that while eventually you have to worry about, or you have to think about the parallelism in your algorithm, a first step can be just to take the sequential code, basically convert it into a kernel, let it run, and then start optimizing from the kernel itself. Okay, a little bit of visuals. So here we have a bunch of these individual threads that are executed on the device. Now these threads are, there's a hierarchy of these threads on the GPU. So we have this number of individual threads. They're actually grouped into so-called thread blocks. And these blocks are grouped into a grid. So sorry for all these words, but it's important that you get used to this CUDA lingo. So basically, a kernel that executes on the GPU is executed as a grid of blocks of threads. You just get used to that. And now just to sprinkle in a little bit more salt into this soup, there's an important concept, which are the warps, which says that the threads that are within a block are not executed independently, but they are grouped into these groups of 32 threads that are executing in lockstep. Now that's a technicality, and in theory, warps are not part of the CUDA model. So when you go back to the old documentations of whatever, CUDA 1.0, it doesn't even talk about warps. So from a philosophical point of view, the model itself doesn't need warps. But it turns out that if you're looking for very high performance, it's important that you keep in mind that under the hood, on the hardware, these instructions are actually executed in blocks of 32 threads at a time. And so this brings us to the question of how are these kernels executed? And how does that map to the hardware pieces? If you remember, Alistair had up a picture yesterday about how a Kepler GPU, for instance, is organized on a technical level, on the hardware level, right? And so he showed this picture where I mistakenly said that there was 15 SMs, and it's actually 14 SMs in a K20X. So these are these streaming multiprocessors, and so you have one or multiple GPUs that consist of these streaming multiprocessors, and each one of these streaming multiprocessors has a certain number of CUDA cores. Now, this is almost an exact reflection of the programming model, or to put it differently, the programming model is a reflection of the underlying hardware, where a CUDA thread is mapped onto a single CUDA core, and for the entire duration of the execution of a kernel, it's going to stay there. And a CUDA thread block is mapped onto one of these streaming multiprocessors. And again, a thread block, once it's being launched, will stay on that streaming multiprocessor. And then finally, you have the grid of all these thread blocks that is being mapped onto one or multiple, well, actually only onto one device, but onto multiple streaming multiprocessors. Now, you may wonder, why do we need this separation into threads and then thread blocks, right? If you think of MPI, MPI is just flat. You have COM world, and everybody can talk to everybody if you want to. But that also comes at a significant cost. Global reductions, for instance, operations where you need to have everybody communicate with each other, becomes increasingly more expensive if you increase the number of MPI ranks. And so that would be exactly the same for CUDA, when if you had a mechanism that would allow all threads to communicate with each other, it would be prohibitively expensive to do that. So it was a conscious design decision to say, okay, let's just make groups of threads to cooperate, and let only those communicate with each other, and basically don't provide a mechanism to let individual groups or individual threads within different blocks communicate with each other. Now, the way that threads can communicate with each other is this shared memory. So it's a piece of memory that sits on each one of the streaming multiprocessors that it can be accessed by all the threads within the same block. And so these threads can then use shared memory to exchange data, or they can synchronize with each other, or so basically do all the mechanisms that are necessary for cooperation. Now, one of the other advantages of breaking up your problem into these blocks of cooperating threads is that it gives you automatically scalability. Think of the following situation where you want to launch a grid consisting of 8 blocks. Well, the CUDA model doesn't say anything about when these blocks are being executed. So depending on the type of hardware you're sitting on, you might be on a device that has 4 streaming multiprocessors or 14 streaming multiprocessors. Well, these blocks will be mapped onto the available SMs, and in this particular case, it will take 2 units of time. Now, the same code can also run on a GPU that only has 2 SMs. It will execute correctly. It will just take a bit longer because you have only half the resources. But given that you already, as a programmer, had to break up your parallelism into these individual blocks of cooperating threads, you're guaranteed that the code will still run even on a different architecture. Now, to come back, we have the grid of blocks, of threads. So when you write the code of an individual thread, you have to have some form of identifying like where in this mass of threads you are located. CUDA provides a various identifiers to determine your ID, your identity. So first, the threads can have up to a 3-dimensional identifier. The blocks then are arranged in a 2D grid. And this configuration is determined at runtime. Now, you may wonder, why do you need 2 or 3-dimensional threads or 2 or 3-dimensional grids? The idea here is that you can easier map it onto your algorithm. For instance, if you're working on a DGEM matrix product, well, your entire algorithm is already working on a 2D array. So it might be easier for you to write the code using 2D thread indices instead of 1D thread indices. On the other hand, if you're working just on linear arrays, it might be easier to just use 1D thread indices within a block and have a 1D grid of blocks. So that's really problem dependent. The variables that allow you to identify your position within the grid are called thread index and block index. So these are the unique indices for each thread and block. And you can also determine the block dimension and the grid dimension, which is useful to then give you the global position of your individual thread. Now, this is kind of jumping ahead and a little bit of syntax. Like, how do you launch a kernel? How do you, quote unquote, call this function that runs on the GPU? The way to do that is this triple bracket notation, this chevron notation, that takes the configuration of your grid. So basically, the first parameter says, how many blocks do you have in the grid? And the second parameter says, how many threads do I have within a block? And here at the bottom, we just see, like, it's a bit an unfortunate example because it's twice 16 by 16. But in this case, we launch a grid of 16 by 16 blocks, each block consisting of 16 by 16 threads. Or in the second case, we just launch a 1D grid consisting of 32 blocks, each block consisting of 512 threads. Now, how do the kernels themselves look like? Well, you have an additional CUDA element, which is the attribute global. This says this function is visible both to the GPU as well as to the CPU. And in this particular case, we have a minimal kernel that just takes a pointer. In this case, it has to be a device pointer, so a pointer pointing to a location to memory on the GPU. And we initialize this to a value. Now, that's a fairly trivial example, and also imagine what implications it has. Imagine if we would launch this kernel on a grid of, as we had before, 32 blocks, 512 threads per block. This would mean we have 32 times 512 threads, all of them trying to write the value 13 into this one location, right? So even though you have a sequential program here in this kernel, it is being executed by all the threads that are being launched in the grid. A slightly more interesting case is where we initialize an array to a certain value, to an integer value. And so again, we're pulling in the device, a pointer on the device. And now we compute the index of each individual element that needs to be initialized. And this is a fairly common pattern that we see here, right? You're saying my personal index, the index of one given thread, is the block index times the width, the dimension of the block, plus the thread index within this block. So this pattern, in one form or the other, is something you will most likely see in pretty much every kernel that you write. Here we just go through an example of incrementing an array of elements. So we have an array, 16 elements. And let's break it up into a block of 4 elements each. So we have 4 threads, 4 blocks, and 4 threads each. Here it just listed out all the individual indices and the thread indices. Conceptually trivial, but it's something where when you write the kernel, maybe it's just me, but I still have to think like 1.5 times about what exactly is my index now, my global index, based on the thread ID, the block size, and the block index. So it's just something that you need to write a few times and then eventually it gets into your brain. And as I said, keep in mind that on the hardware, our width, the minimal width of an instruction is actually 32 threads. So the example that we have here, where we give each block just 4 threads, will result in 28 threads on each streaming multiprocessor that simply sit idle. So you want to have at least 32 threads in a real code per block. Here just a comparison. Oops, this arrow has been stretched a bit too far. How this would look like in a real code. Right, on the left-hand side, we have the pure CPU program. So you have your main, and then you call a function where you're incrementing an array A that contains n elements with the value B. And so in this function, you have your loop, and you're incrementing A subindex with B. Now, the corresponding CUDA program is not significantly different. The only difference that you're seeing, or the main difference, is that the innermost loop got removed. Right? So the innermost loop got removed by the grid of threads that you're launching. So each one of the threads can identify itself, and then it just does a safety check to make sure that you're not writing out of bounds, and then updating the element A subindex. And oops, there's the wraparound down here. There's the launch of the kernel, where we say our grid dimension. Well, we just define some block size, whatever, 32 elements for 32 threads per block. And we compute our grid as the number of elements divided by the block size. One dimension higher, as I said, if your problem is suitable for a 2D thinking, like in a matrix case, well, you may want to have a grid that consists of 2-dimensional blocks and is arranged in 2D in a 2D grid. All that happens is that your index calculation becomes slightly more convoluted or a bit more complicated. But again, at the core, it's exactly the same as we did in the 1D case. You have your thread index, you have your block index, you know the number of threads within a block, so you're just computing the linear index for each one of the dimensions. Okay, so far we've talked about what kernels are, how you break up the problem, and how you can configure your grids. Now, as I said, CUDA also defines the memory model. So you have various different memory spaces that you can take advantage of. And it's also worthwhile to just have a look at it. At the very core, each one of these CUDA cores has a set of registers available. That's where the actual computations take place. On top of that, each one of the threads has access to so-called local memory. This is a chunk of memory that exists on a per thread basis, is private to each thread, but it's not as fast as registers, but it can be pretty much used similar to registers. So each thread has access to its individual set of local memory. Then you have shared memory. That's the one that the threads share within a block. Shared memory is also pretty fast, not quite as fast as registers, but certainly faster than global memory or local memory. The lifetime of shared memory is similar to registers and local memory. It's just the it's actually the lifetime of registers and local memory is determined by the lifetime of each individual thread, and the lifetime of shared memory is determined by the lifetime of a block. And then finally, you have global memory. So that's the memory that sits on the GPU device. That's what OpenACC makes so much nicer, is the transfer to this global memory and back. So that's the 6 gigabytes that we currently have on the K20X. So the lifetime of that is just for the entire duration that you have allocated memory on the device and before you free it again. So that is, the lifetime of global memory is not limited to a individual kernel execution. And then finally, we have host memory, and now this is slightly outdated, a slightly outdated slide. There is mechanisms of making host memory accessible to the GPU, also the other way around, to write directly into GPU memory. But those are features that add a little bit of convenience to the programming model. But if you want to get good performance, it's better if you start with thinking about just assuming that these are separate memory spaces. And then maybe if there's no way around peeking and poking from the other world's memory, then at that point you might want to go into those details. So for simplicity, just assume host memory and GPU memory require an explicit transfer of data between each other. A bunch of diagrams. I think we have covered pretty much all of that. Yes. So that's it. So let's look into actual code. So when you write a piece of GPU code, the actual kernel is just one part of it, but you also have to worry about the data motion to and from the GPU. Very helpful, and with lots of examples, is actually the C programming guide. Unlike previous versions of CUDA, we now have everything online. So at docs.nvidia.com, you can find the entire documentation, and programming guide is just one more of these documents. So no more need to send around PDF files. Memory allocation and release. Very simple to, or very similar to allocation and release of memory on the CPU side. So you have a CUDA malloc, you have a CUDA free, and if you want to initialize your data, you have a CUDA memset. Now CUDA malloc, unlike the malloc on the host side, where you basically have a malloc of a certain amount, and you get a pointer back and you assign it to a variable, CUDA malloc takes a pointer to a device pointer. The reason for that is that all the CUDA functions return an error code. And so, yeah, in order to not break that, that concept, it was decided to actually stick to a slightly different syntax than in a regular malloc you would have on the CPU side. So yeah, you CUDA malloc, whatever, a chunk of bytes, and you get a pointer that sits on the device to that amount of memory. Data copies. So once you've allocated memory, you can move data from the host to the GPU or the other way around. So the main call for that is CUDA memcopy, where you provide the destination pointer and the source pointer of your data, and the amount of data you want to move around, and the direction that this transfer has to go. Host to device, device to host, device to device, or host to host are options as well. Now, again, it's funny because CUDA has been around for, close to 6 years now. And a lot has changed, not only on the hardware side, but also on the side of the demands from the users. And when CUDA came out, there was nothing like unified virtual memory and or unified virtual addresses. And so, yes, you explicitly had to tell CUDA memcopy in what direction that a copy would need to go, because there was no way for the runtime to figure out if this pointer points to an address on the device or if it points to an address on the host. This has changed in the meantime, and there is actually an interface now to CUDA memcopy where you don't need to specify the direction anymore. It's just the first argument is the destination, and the second argument is the source, and it looks into the addresses and determines based on that in what direction the copy needs to go. It's small things, but they're all geared towards making life easier for the developers, that you have to worry a little less about such technicalities. Also, when you think back to Alistair's talk about the async clause in OpenACC, well, CUDA memcopy is actually a blocking call. So it's a synchronous call. You know that once CUDA memcopy returns control to the host process, it's done. The data is on the GPU. There is non-blocking memcopies, as I said, to support features like async in OpenACC, and they can help you hide the data transfer latency. So, your time to do something. As I said, I think it's very helpful that everybody has written at least a minimal CUDA example. So I would suggest you log on to TODI and write a small program that takes a string, moves it to the GPU, and gets the string back and prints it out. Okay? Also, let's see. In this directory here, there's some. Pardon?
You should have protected them.
They're protected? So it should be possible to access the data on. Oh. Oh, okay. Right. So it's project CS staff courses and then CSCS_XK7. Oh, did I? No, I don't even mention it here. So there's the slides, and there's also samples, sample 1 to 5, I think, that have a basic makefile. But let's see if I can do that here. Oops. So, do you guys have, did anyone try to copy that tar file and succeed? Okay. So the first thing that you need to do is to make sure that you have the CUDA toolkit module loaded. So, and if you then list the modules somewhere, it should show up as CUDA toolkit. And that will give you access to the compiler NVCC, which is the CUDA compiler that happens to be sitting somewhere under opt Nvidia. Now I've, as I said, I've already sample1.cu. So by convention, CUDA files usually end with the extension .cu. And that contains this very basic example. So please feel free to play with it yourself or modify as you like, or even better, write it from scratch. It's helpful to do that. So what do we have here? In our main program, we create this string. And the first call is to malloc memory on the device. In this case, we just take a buffer of some 100 elements. So this is certainly not the way that you would want to write a CUDA production code, because we simply ignore any kind of error checking, or we have hard-coded numbers and so on. So it's really for sake of simplicity, we just ignore all that. But we have the device pointer, the device message, that finally will point to this chunk of memory that we have on the GPU. And then we copy from the host to the device these n elements or n characters. Now, as you can tell, this is already very, very ugly because our message in is actually shorter than n. So we will see this afternoon that you can use tools to determine that out-of-bound access. And then we do the same thing, the reverse direction, and finally print out the message. So if we are lucky, the make sample sample1 should work. And so here you can see the invocation of NVCC. So it's basically NVCC and then the source file. And similar to every other compiler, you can provide the output file. And one thing that's somewhat special for TODI is that you want to specify the architecture that you're compiling your code for. The thing is, again, legacy-based. By default, NVCC produces code for GPUs that are probably not even sold anymore, so-called CUDA Compute Capability 1.1. With this architecture, SM35, you're saying that the compiler is free to produce code that can make certain assumptions about capabilities that you have. and 35 is the compute capability for a Kepler device, as we have in the XK7. Okay, in order to run this, we first need to get in an allocation. I have a bunch of Slurm scripts in there, so sample 1.sbatch, but as we're allowed to use interactive, the nodes interactively, let's do it. So it's res equals course. That's all written down on the sheet that Neil has distributed yesterday. Nodes equal 1, and time equals, let's see, 5 minutes. And so I got now my allocation, but I'm sitting actually still on the head nodes of 30. So if I want to run my application, I now need to use apprun -n and sample 1. And yeah, the program has worked correctly. My message in was printed out. It went to the GPU and came back, and I got the result printed out as well. So just once more, what have we done so far? Oops. We haven't launched a GPU kernel yet. All we've done is we've allocated memory on the GPU, we've transferred data there, we've got the data back, and we've printed it out, and we cleaned up after ourselves. We did a CUDA free. Okay. Oops. Now, next step is obviously that we want to write a kernel that executes on the GPU. There's a few things to keep in mind. The kernel can only access GPU memory, and again, with some exceptions. But ignore those for now. Number of arguments have to be constant. Return type has to be void. So it's basically procedures, if you like to think in those terms. So those are the limitations for kernels. And then you have a set of qualifiers for each one of the functions. We've met one before. For a kernel that is visible on both the host and the device, you need to provide the global attribute. And then there's the ones that allow you to specify that a certain symbol is only visible on the host or only visible on the device. So $_host says that this function is only visible on the host. Well, that's actually the default for all the code that will be executed on the host itself. So there's no real need to specify the host attribute. The device attribute can be useful. That's for functions that will be only called from within a kernel. So these functions that are that carry the attribute device, they will not be visible on the host. And then finally, you have the identifier and the dimension, the built-in variables for the kernel that help you to identify each thread individually. Now, those were the quantifiers for the functions. Now, you also have a bunch of qualifiers for the individual variables. The one is the device qualifier that says that this variable sits on the device. So you can create something like static variables that will, for all the time, sit on the GPU. You have the possibility of labeling something as constant, or then, most importantly, the shared qualifier that allows you to say that this variable will be shared amongst threads in a thread block. And if you, within a kernel, if you have a variable that doesn't carry a qualifier, they either end up in registers or they will be put into local memory. As you remember, local memory is this piece of memory that actually sits in global memory, so it has slow access times, but is available on a per thread basis. We talked about launching kernels on the GPU, right? Triple chevron notation, the first argument being the dimensionality of the grid, so the number of blocks that you have. The second argument being the number of the number of threads you have within a block. There's actually two more arguments that you can provide. We'll skip them for the moment, but yeah, just in case that you stumble across a kernel launch that carries more arguments. The third one is the amount of shared memory that is used by each one of the blocks in case the amount of shared memory is not determined at compile time. So imagine you would write a kernel that does whatever reduction on different types of structs. So on variables that have different sizes, and the size of this variable is only determined at runtime. Well, this would require that you determine at runtime how much shared memory that you have. And there is actually a mechanism with this mechanism, with the third argument, you can tell the kernel, hey, by the way, you now have 4K of shared memory available per block, or you only have 1K of memory available. Making sure that you're then not trying to use more than the amount of shared memory that you were given at the kernel launched, that's the responsibility of the programmer. But this at least allows you to dynamically adjust the amount of shared memory that you use per block. And the last argument is the so-called stream identifier. We will come back to streams in a while, but as Alistair has explained before, streams is a mechanism of scheduling individual kernel launches in separate groups. And you basically allow kernels from multiple streams to execute concurrently. So there is no guaranteed ordering between kernel launches in separate streams. But you are guaranteed that kernel launches within the same stream are executed in sequence. So this gives you a way of, again, making more advanced scheduling patterns of your kernels. All right, next hands-on exercise. We have now this kernel called hello that just transfers the string hello accelerator to the GPU. Now let's write the kernel to uppercase this entire string. So convert each character into an uppercase character. Oops, my allocation has been revoked. And again, we have this, as this is not really a typing exercise, I have the same, a prepackaged version of this here. When you look at the main program, it's exactly the same as we had before. But we now have this kernel launch after the transfer from the host to the device. We launch a kernel, and we're just using a single block, and each block contains n threads. N being the number of elements, well, sorry, n being just 100, kind of a default buffer size that we assumed. Okay, and what else do we have as arguments to the kernel? Well, we need the device pointer, and we tell it the length of the string that we're working on. Right? Our buffer is 100 element long, but the string that we're working on is only, 15 characters long or so. Okay, so that not a whole lot has changed here. Now, here is the kernel. We have a character pointer, a byte pointer called message, and we have a certain length of n elements that we passed in. That's the 15 or so characters that we care about. And then we identify ourselves. Given that our grid is only one-dimensional, so we have only one-dimensional, our threads are one-dimensional within a block, and we only have a single block. All we need to do in order to identify an individual thread is to look at the thread index.x. Right? This would become a bit more complicated if you had multiple blocks. Then you would need to have a block index.x times the block dimension.x plus this thread ID. But given that we're working with small strings, that's perfectly feasible. But now remember that we launched a kernel with 100 threads per block. But we only care about these 15 or 16 characters. So that's why we have a check here saying that, oh, if my thread index is smaller than n, than these 15, only then you're doing the uppercasing. And so here's, if you remember the ASCII character set, the characters differ by 32 between uppercase and lowercase. So if the character, so you're reading in here from the message, from your string, the TID character, so a certain character within the string, each thread. And if this character has a value higher than 96, then you actually have your probability is high that you have a character. And so all you do then is to subtract 32 from it, and you have the uppercase case. So yeah, ignore all the details here, what happens here exactly. But the key is that each thread loads a character from the string, and it writes it back. And that's it. So, and again, yes?
How I can determine how many threads are in one block?
There's the other.
Here you put 100.
Right. So there's the
1,000, 10,000, whatever.
So there's two facets to your question. One is, how do you determine it as a kernel, right? And so as a kernel, you have additional built-in variables. So, right, you have the thread index.x, and you have the block dim.x, which is the block dimension. Remember, the threads sit within a block. So the dimension of a block is the number of threads that are inside this block. So blockdim.x is the maximum that you could expect for thread index.x. Now that's kind of the technical side. How do you determine the thread and finally the global index? The other subtle question that you had was, how do you determine how many threads you actually want to launch? How big should n be here? How many threads do you want to have per block? And that's another one of those questions that is very hard to answer in general. It depends on your application. It depends on your algorithm. There's certain limits that are imposed by the hardware, certain numbers that just don't make sense to use, but you're perfectly free to use them. Or you could do that. So thread index can go up to 65K. Block IDs can go up to 65Ks in 3 dimensions. So you can have a grid that's larger than probably any available memory that is in your machine. But yeah, the exact value of how many blocks that you have really depends on your algorithm. And again, the number of threads within a block is given by the question of how many threads do you need that cooperate. Right? In this case here, well, it doesn't matter because they don't cooperate. But in case you had an algorithm where they would cooperate, it matters, and that then defines the number of threads that you want to have within a block. And there's tools and other heuristics that you can use to determine the optimal size of the number of threads per block. As a rule of thumb, as we said, the number of threads per block should be a multiple of the warp size, simply for the technical reason that they are being executed as full warps. So it should be a multiple of 32. For Kepler, you probably want to have something like 128 or 190, whatever, 96 or so, 92. Somewhere around there. Let's say 128 to 256 is really, as a rule of thumb, is a good number of threads per block. Okay. And what did we do here? So I got my allocation again. I can do my make sample too. And I do an app run minus n1 of sample 2. And we get the whole thing uppercased. Woohoo. Oops. Nope. Now, just as a final piece, using shared memory, how can you do that? Here you have a line of code, how it would look like in your kernel. So you have the qualifier shared, and you just declare a variable that then means that this variable is accessible from all the threads within a thread block. Oftentimes, this variable is an array, but it might as well be just a scalar. Now, shared memory is a limited resource. And when you're tuning the performance, you have to be careful about how much shared memory that you're allocating per block. On devices up to now, you have up to 48 kilobytes of shared memory on a block. So that means you can at max allocate 48 kilobytes of data. However, the architecture of the GPU wants you to use more than a single block per streaming multiprocessor, right? The way that you're hiding all the memory access delays, the latencies for accessing global memory, is that you're swapping in more work so that to keep the GPU constantly working, and if one of the threads has to stall because it waits for memory for an access from global memory, there should be more work ready to keep the GPU busy. So if one of your blocks uses up all the 48 kilobytes, there's a fair amount of chance that you're underutilizing the device simply because you cannot have sufficient work that keeps on going on the GPU, on each one of the streaming multiprocessors. So that's another one of those parameters similar to the number of threads that you want to have per block that can help you determine the performance of your algorithm. So by picking the right amount of shared memory per block, you can affect the performance. In addition to shared memory, or once you have cooperation, you also need to make sure that you're synchronizing. And so there's a primitive called sync threads that allows you to make all the threads within a warp stop until the synchronization point is reached. And I'm sure Salaf is here to tell us that there is warm pizza outside. So let me just... Yeah, actually, I have the last exercise. So that's a good break point here, which just says that we should. Oops. Oops, sorry. So instead of hello accelerator, I should have a hello network. Hello? Yeah, exactly. Well, you should all have access to that sample as well, but yeah, I can't move my cursor anymore. But anyway, you see here what happens in the kernel. We now declare a local array of characters as shared, and for the n threads that are, oops, I finally got it moved. Well, anyway, so each thread loads from the global memory string into this shared memory, and then we access not only our own character, but also a character to the left of us. Oh yeah, I should have said what the exercise tries to do. We're trying to uppercase only the first letter in a word. So basically the way you do that is that you're looking at your character, and if the character to your left is a space, then you uppercase it. And so that's exactly what we do here. So we load the string into the shared memory. We sync thread, because we have to make sure that all the threads have actually loaded this stuff into shared memory. And then if the shared memory character on the left to us at an index 1 minus us is a string, is a space, then we convert our character into an uppercase character. So it's somewhat contrived example, but I mean, that's exactly what you do in many stencil applications, right? It's a finite difference scheme. So it's something that you will most likely encounter in real life applications as well. So I would suggest we break here. Yeah, I think there's, yeah, that's basically the end of the, yeah. So let's break here and then come back to somewhat more advanced Kepler and CUDA 5 features. Okay, thanks. The last part of this presentation, which is not very fundamental stuff, but just one slide that I want to show. Again, given that we have so many Fortran programmers here, just to give you a feeling of how Fortran looks like, for instance, in PGI's CUDA Fortran. As I said, the one approach is the mixed language approach. So basically on the Fortran side, you have a call my func. Oh, and there's a C missing. Call my func, and then you have an extern C function that then launches the kernel. So that's one approach. The upside is it works with any compiler, fairly straightforward. The only problem is that you have to worry about the calling conventions. That's whether you need to underscore the function name or not when you call C from the Fortran side. And you have to worry about two different languages, so that can be a bit inconvenient. Now with PGI's CUDA Fortran, you have extensions to Fortran that, for instance, if you have an array U that has a certain dimension, you can create arrays that have the attribute device that will live on the GPU. And so simply by assigning U to A, you're copying data between host and GPU. You have a mechanism for calling kernels. So CUDA Fortran also supports the triple chevron notation. So otherwise, those are simple functions with now an attribute called global that it identifies these subroutines as kernels. So this is not meant to be an example. It just should give you a bit of flavor, a feeling for how it looks like to write CUDA Fortran code. The upside is definitely that you have a very Fortran-like approach to CUDA. The downside is that it's currently only supported by PGI. But PGI's compiler is available on TODI, so you can give it a try there if you just want to play around with some examples. Okay, so what I didn't talk about this morning was anything about optimization. And frankly, there's a lot of talks out online about doing optimizations in general, CUDA optimizations. There is lots of material. Please just go out and Google for whatever, CUDA optimization, and you will find various presentations. I also can talk about streams in very much detail, so we'll come back to that. And the multi-GPU programming is another thing that I simply ignored so far. The way that we view the programming environment for GPUs is basically put on 3 pillars. One of them we've been talking about extensively is OpenACC, which is kind of in between low intrusion and maximum intrusion into your application, or maximum flexibility, if you want to use a euphemism. Programming languages, that's what we're going to talk about is with CUDA. But keep in mind, there's a lot of libraries out there that have been developed for GPUs specifically that may already be solving the problem that you have at hand. This is just a few of those put out, of those libraries that are currently available. Many of them are provided by NVIDIA itself, like cuBLAS comes with the toolkit, cuRAND for high-quality random number generators, for sparse linear algebra, what else, FFT. So for many of the very basic algorithms, there's libraries that you just plug in and they run on the GPU. And then there's more specialized ones, like the Visible, which is a image processing library, and commercial ones as well. So there's a zoo of libraries out there. So before deciding to write a lot of code yourself, please go out and have a look at these different libraries. Oh yeah, actually there is. Yeah. Ah, cool. So now when talking about CUDA, it's important to first figure out what is the actual model, and then only later on dive into the syntactic elements that are being introduced. So we're going to change gears now a little bit. There has been quite a lot of talk on OpenACC and on the way how to accelerate an application with GPUs without changing the control flow of the application too much. So what we're looking at now is how to get the best performance out of the GPU if you're willing to actually write code for the GPU yourself, so by programming in CUDA. Just to give a brief overview, I mean, you have the outline of what's going to happen during the rest of the afternoon or of today. Basically, this first 1 hour presentation is going to be basic CUDA. We do a little bit of hands-on work because I think it's important that everybody has at least once in their life written a CUDA program, a small one by hand. So it's not going to be very exciting, but it's just a little exercise. And then in the afternoon, we talk a bit more about Kepler, so the device that's currently installed in the XK7, Kepler and CUDA 5, which is the latest CUDA version, what kind of features it has, and so on. And then after that, we will talk a bit more about debugging tools, performance analysis tools, and so on. I'm not at all committed to the schedule. So if you have any questions, or if you have any particular pieces of information that you're keen on, let me know. This is your time, and you should get the most out of it. Okay, right. What on the NVIDIA side, the parallel code that is then being farmed out to the GPU. The parallel code executes on the GPU, and it can be one or multiple ones. That's then up to your particular application. The code that runs on the GPU is called a kernel. And the entire GPU executes many kernels or it executes one or a few kernels with many, many threads. So a thread is an instance of a kernel running on the GPU. Now these threads are not the same as the heavyweight POSIX threads that you have on the CPU, but they are basically just individual lanes in a vector instruction that are being executed. So again, just for the terminology, we talk about the CPU or the host, and the host executes functions. And we talk about the GPU or the device, and device executes kernels. So depending on what you're listening to, you can already, when we talk about the kernel that it's something that executes on the GPU. So we've covered that the kernel is a function that is being executed, and it's executing an array of these threads in parallel. Each one of these threads has a way to identify itself. So basically to identify the array index. In CUDA syntax, it's called thread IDX index, which is a three-dimensional struct that, and the X component is the first dimension of the thread index. Now, all threads that execute a kernel execute the same code, but they can take entirely different paths through this code. So you can branch based on your thread ID. You can perform entirely different operations based on your individual ID. Now, whether that performs well or not is a different question, but you can do that. So that simply means that while eventually you have to worry about, or you have to think about the parallelism in your algorithm, a first step can be just to take the sequential code, basically convert it into a kernel, let it run, and then start optimizing from the kernel itself. Okay, a little bit of visuals. So here we have a bunch of these individual threads that are executed on the device. Now, these threads are, there's a hierarchy of these threads on the GPU. So we have this number of individual threads. They're actually grouped into so-called thread blocks. And these blocks are grouped into a grid. So sorry for all these words, but it's important that you get used to this CUDA lingo. So basically, a kernel that executes on the GPU is executed as a grid of blocks of threads. You just get used to that. And now just to so first, I just want to talk about the overall model. This is somewhat of a repetition what Alistair has already mentioned yesterday, but it's so fundamental it might be helpful to just hear it a second time. So what is CUDA? Actually, since CUDA was introduced, there has been a shift. Originally, it was a subset, well, it was C with extensions, and somewhere in the various versions of CUDA that have been released, it has moved to C++. So the NVCC compiler, the CUDA compiler, is now a full C++ compiler. CUDA itself is C++ with some extensions. I know that, it was about 50% of the people here are native Fortran speakers. Fortran support at the moment is only via mixed language approach, or alternatively with the PGI compiler that has a Fortran CUDA, its own CUDA Fortran standard. The goal of CUDA is to scale to hundreds and thousands of threads, but without having to worry too much about the details of how then these threads interact with each other. So the developer is still focusing on a sequential program that they're writing. And as I said, CUDA defines not only the programming model, but it also defines some of the architectural concepts, like the actual memory model. So how does a CUDA application look like? Well, it consists of a single source file or multiple source files, but you basically have an interleaving of serial code that runs on the host CPU, and